Good afternoon. How is everybody today? Good? Still here with us at reInvent on Wednesday. Hope your week is going great. We appreciate you joining us today. My name is Justin Pirtle. I'm a serverless solutions architect here at AWS. And today I have the privilege of being joined by Ranga Muvavarirwa, Vice President of Entertainment Technology, and Director of Software Test Engineering, Anushree Shenoy, of the Comcast X1 platform. And in today's session, we'll be first giving a brief overview of serverless stream processing. So for those not familiar with streaming and Kinesis, we'll do a quick intro, but this is a 300-level session, so we won't go in too much there. We'll spend the majority of the time diving deep into a serverless streaming data pipeline and the key functional areas of the pipeline and best practices you can implement in your workloads for each of those areas. And then finally, to give you perspective and context of how this can be done at scale in production, we'll have Comcast and the X1 team share their journey of how they've implemented a real-time serverless telemetry pipeline to power their Canary deployments at Comcast. So first, how many of you are using streaming today in some form? Okay, about a third of the room. Okay. So for those that aren't familiar with streaming, here at AWS, streaming we think of as having 4 key characteristics. So the key thing first is it's high volume and it's continuous data. And because the data is continuous, emitted in smaller intervals, right, with more data, a lot of times a single message in itself doesn't make sense. So the ordering of the messages in their entirety make the natural meaning of the stream and the data within the stream. And then, of course, the key thing about streaming you're going to hear again and again today is it's low latency, right? So why is this so popular? Fundamentally, in the batch processing world, the world where we've had for many years ETL jobs that run hourly or daily, the reality is data loses value over time. So in the batch processing world, where you might have gotten hourly logs or daily clickstream views, wouldn't it be more powerful if you could get real-time metrics that could power your Canary deployments, like you'll hear with Comcast today? Or if instead of actually seeing what people clicked on your website yesterday, what products were trending, what if you could actually change the behavior of the customer while they were still on the site by tying in real time to your recommendation engine, suggesting a product they might purchase and actually grow your revenue and not lose the sale? This is just some of the use cases of streaming that we see that our customers of AWS are pursuing today. Now, the other key concept to go along with streaming that we certainly will be talking about today is the serverless operating model. So for those of you less familiar, serverless at AWS means 4 things. Fundamentally, there are no instances to provision or manage, right? And you're paying for value, so you're only paying when something is running that you're actually receiving some benefit from. So in the case of streaming today, as you're going to see, if you don't have a message in the stream, we're not running the consumer and the compute to process the stream. Only when there's a message in the stream would we do that. And then, of course, automatic scaling, high availability, and security are all built in. So with that definition, the serverless portfolio at AWS has many different products. And so today what we'll be focusing on more are Amazon Kinesis and AWS Lambda. And for those of you less familiar with Lambda, Lambda is our function as a service compute offering. So we won't really spend much time talking about Lambda. We'll talk about how Lambda can be used with streams itself and dive deeper on the best practices there. So first, Amazon Kinesis. How many of you are using Kinesis of some form today? Okay, about a fourth of the room. Okay. So for those that aren't familiar, Amazon Kinesis and streaming data in general at AWS has several different offerings available. So Kinesis as a family has 4 offerings. 3 of the products are focused on data streaming. So we have Kinesis Data Streams, Kinesis Data Analytics, Kinesis Data Firehose, and for data streaming in not a serverless way, but in a way that may be more compatible if you're lifting and shifting existing workloads running on Apache Kafka. We have the Managed Streaming Service for Kafka, or MSK for short, which we won't dive into today because this is about serverless streaming, but want to just make sure you're aware of that since you can simply lift and shift many Kafka workloads. So the rest of the Kinesis family we'll actually dive into in depth each of the members of the family and how you can use them in their best capabilities. But to put a logical framework on it all, when we look at a serverless data processing pipeline, we see kind of 4 key stages functionally that you're dealing with, 4 domains. First being ingestion. So how are you going to take that data from your producer, whether that's a mobile app or your web servers or whatever it may be, ingest it at scale, right? And then you're buffering it and ingesting it, and you need a way to actually process it to make sense of that data. And then, of course, the results of the processing alone, just with streaming, wouldn't be useful if you couldn't persist them in a durable manner for long-term storage, and that's the storage considerations. And then finally, once you reach your storage destination, you have many analytical tools and real-time business intelligence types of use cases you may want to apply on the data. So we're going to dive into each of these functional areas and talk about best practices that apply. So first is ingestion. So in the ingestion world, we have 2 services available from AWS that you can use. There's Kinesis Data Streams, and there's Kinesis Data Firehose. And first up is Kinesis Data Streams. So with Kinesis Data Streams, it is a managed message buffer of ordered messages. And the way it scales is you have the concept of shards. So every stream has at least 1 shard, and every shard gives you throughput of 1,000 records per second, or 1 megabyte per second of ingestion throughput. So if you have a whole lot of data, you're going to want to have a variety of shards, a large number of shards, to make sure you can always ingest all that data at once and be able to scale to whatever need you need to get to. But the key thing that goes along with Kinesis Data Streams is you always need to have a consumer of the stream. Just pulling in the messages and buffering them without a consumer to read them means they would go nowhere, and they just fall off the stream eventually. So on the consumer side, you have a variety of choices. You could use a Kinesis service itself. So you'll see today how Kinesis Data Firehose and Kinesis Data Analytics can read a Kinesis data stream. But in addition to that, you could also use a managed Hadoop-based processing framework, maybe Apache Spark, whether it's running on EC2 or Elastic MapReduce. You could run your own custom applications. And so for those, you could run them perhaps on EC2 with the Kinesis client library, or what we'll be focusing on today, AWS Lambda. So our function as a service offering and how that can directly run your custom business logic to process the stream. And so Firehose, in comparison, the difference here, Firehose still deals with ingestion, but Firehose also deals with delivery. So in the Firehose world, there is no concept of a consumer to write. You're actually just defining and configuring what destination you want to write to. And so Firehose supports writing directly to data lakes using Amazon S3, Amazon Redshift clusters for data warehouses, Elasticsearch clusters for our managed Elasticsearch service, or Splunk. And if you're going into any of those destinations, Firehose is going to implement best practices around that delivery to the destination on your behalf. No code required, just some configuration. So that's Firehose. So a common question is, when would I use one? When would I use the other, right? And perhaps together, right? They're not mutually exclusive. So Amazon Kinesis Data Streams is for use cases that require custom processing or sub-second latency. If you need very, very low latency, Kinesis Data Streams will allow you to achieve that. Whereas Kinesis Data Firehose is for use cases that are going to a managed delivery destination, the data warehouse, the data lakes, and more that I mentioned. But the key thing here is it has data latency of 60 seconds or higher. So if you're using Data Firehose and you need really real-time metrics, it may be not the right choice for you. Now, regardless of what you use, you have a variety of ways to write to these streams. So all of them are basically able to be authorized with the Identity and Access Management service of AWS. But you could write to them directly with an API call. So we have a put record API and a put records API call. You can put multiple records in one call. And those you could do direct from our AWS SDKs. So the mobile SDK, the mainstream SDKs for many different languages, those are available. AWS services themselves, like CloudWatch Logs, API Gateway, EventBridge, CloudWatch Events, all of these natively can write to Kinesis as well, and they do so via the API calls that I mentioned. But in addition to those, we have some higher-level offerings available that you could just drop into your applications. So you have the Kinesis agent. So for any of you doing web server log aggregation or any kind of log aggregation, all this requires is installing a local agent, configuring which file paths and file types you're looking for, and it will automatically batch the log files and effectively tail them and write them to the stream in real time. Now, the Kinesis producer library, not only can it write to the stream in real time, but it implements a lot of other best practices, but it does require integrating it code level into your applications. And by best practices, the things that it does are both batching, where it's going to take many records, one API call, write them to the stream, as well as something called aggregation. So we'll talk more about this today, but aggregation is another best practice if you have a lot of workloads with very small messages. A single record in a Kinesis stream can be 1 megabyte. So if you're writing a whole lot of small messages, you may need more shards just because you have more than 1,000 messages a second, which is the max for a shard. But what if you could put a lot of small messages into a bigger payload as one message? That's what aggregation is. And that's implemented out of the box with the Kinesis producer library on top of batching. And then these are just the first-party techniques available. You can also use many third-party native integrations, so Log4j, FluentD, Flume, and others. But whatever you're using, you're getting the data into the stream, and that's really the end of the ingestion process. So best practices. At the end of the day, when you look at data processing pipelines, the key thing is you're optimizing generally for one or two things, or maybe a balance of both. You're optimizing for either end-to-end latency or the overall cost of the application. And so when looking at latency, the first thing you want to think about is, do I have enough shards to ingest all of the data I need? If not, you can get an exception and get throttled, right? So you need to have enough shards at all times, but this number of shards is not static. Like anything else with auto-scaling, you can auto-scale your shard count. Now, there are some soft limits that apply on how often you can do this, but many of those soft limits can be raised just with the AWS support case. But if you'd like an example of how to do this with application auto-scaling, for either scheduled scaling or other more intelligent scaling, here's a good blog post that shows you some techniques on how to auto-scale your shards. Now, particularly when you're scaling down, just like any other auto-scaling, you want to be conservative, because you want to make sure you always have a buffer to be able to ingest further messages in a time of a burst, right? The cost side, however, there's different things to think about here. You don't want to have unnecessary shards more than needed, so this is where aggregation, writing a lot of small messages to a single record in the stream, can be very cost savings. At the same time, implementing batching at the producer side will create fewer API calls and allow you to write to the stream less frequently in a more rich manner. So those are just some techniques, but another technique that I think can be overlooked many times that's really up to you as the producer, the one who controls the code writing to the stream, is just the impact of compression and encoding of your messages. At the end of the day, a Kinesis record is a partition key and a payload, right? So you control the payload, which means when you look at the pricing of these services, and you're constrained by the amount of megabytes per second you can ingest, or in the case of Kinesis Data Firehose, where it's just about the number of gigabytes ingested per month. If you're writing less data in terms of overall number of gigabytes, you're actually spending less money, right? So from that perspective, using compression on your payloads, perhaps before you write them to the stream, or writing them with an encoding mechanism that's very efficient and very lightweight, perhaps a binary encoding mechanism, such as protocol buffers or Avro, those type of encoding mechanisms allow your payloads to be very nimble, and then of course with aggregation and batching on top, you need far fewer shards to accomplish the same ingestion at scale. Now, aggregation, as I mentioned, implemented by the Kinesis producer library, we actually leverage protocol buffers as an example of encoding for how we're doing that built into the service. You don't have to define anything, you can just plug in the library to do that. So that's ingestion. Now that the data is in the stream, now we need a way to actually process it. And on the processing side, you have a variety of options. So you have Kinesis itself could be the consumer of the data. We have Kinesis Data Firehose, Kinesis Data Analytics. Both can read a Kinesis data stream. You could also use the Kinesis client library for your own custom application, either on EC2 or on premises, wherever you're running that. You could use a third-party framework. So Apache Spark, yet again, these kind of frameworks, Hadoop-based frameworks, those run not only on EC2, but you could just run them in a managed way with Elastic MapReduce or Amazon EMR. But perhaps the easiest way, the one we'll dive into the most today, is just using AWS Lambda to read the stream. And that's our serverless approach that we'll be using. So why is Lambda so popular? Lambda gives you several benefits when used with Kinesis. Fundamentally, you have no instances to manage. Right? The Lambda service is only going to spin up your code and invoke your code when there are messages in the stream to be processed. At the same time, as your stream scales, as you scale out the number of shards, Lambda will automatically scale with you to keep the perfect concurrency in the processing at all times. Lambda also takes care of all the semantics around handling the checkpointing of reading the stream. Right? You don't have to do any of that. So to show that a little closer, here are the Lambda execution models out there today. For all Lambda invocations, they fall in one of these three buckets. So the poll-based bucket on the right, this is what happens when you take a Lambda function and in the console or the APIs, you say, I'm reading a Kinesis stream or a DynamoDB stream or even an SQS queue. All three of those follow this poll-based approach. And in that sense, what happens is the Lambda service itself has a polar fleet that reads the stream. And every shard in the stream, on a regular basis, the polar fleet is reading. And if a given shard has a message, then and only then do we invoke your code. So you're not paying for your compute to run, just sitting around, long polling, all these kind of things. It's all built in at no additional cost to you just by using Lambda. And Lambda also takes care of the checkpointing. So if you've ever used something like the Kinesis client library or something else, you have to keep track of where you are in the stream. A stream is an ordered buffer, so you have an iterator. You need to keep track of how far you've gotten along in that stream. So to show this end-to-end with Lambda, you have a producer. Right? The producer is continuously emitting data into your Kinesis data stream. Lambda, by default, is polling every shard once per second on your behalf. And then you have, let's say, one Lambda function A. If you've associated that with the stream, and one of our shards is a message, then we'll go ahead and spin up an execution environment or sandbox of Lambda function A's code and actually just send it the message of the records you have in the stream as a simple array in your event. Everything else about the stream, Lambda doesn't know. It just gets your records and its code, and that's it, and the event coming in. Now, you can have more than one function. So for those of you that are familiar with the fan-out patterns can be implemented with Kinesis as well. So you could have multiple consumers of a given stream and a given shard. But you want to be mindful that a shard, just like it has an ingestion throughput limit, on the consuming side you also have a limit. So the limit is effectively 5 reads per second, or 2 megabytes per second. So if you had 5 consumers, that means each of them could only read 400 kilobytes in that second. So for these reasons, you want to be thoughtful about the number of consumers of the stream, or use some of the techniques we're about to discuss to scale even broader if needed. Any consumer of the stream will count against this limit. So in this case, I have 2 Lambda functions, Lambda function A and B. Both would read every shard of each stream every second. So that's 2 right there. And if your payloads are big, that could maybe consume all of your throughput. So it's just something to think about. Kinesis itself will consume the stream, and it would count against that limit of the 5 reads per second. Now, to show that more graphically, here's a stream with 4 shards. And in the 4 shards, we have the Lambda service there in the middle. It's polling each shard once per second. And if all 4 of those shards have a message, and you don't change any of the default behaviors, we will be running 4 sandbox environments of your code, the same code for the same function, at the same moment. So we'll always have at most the number of sandboxes here as the number of shards you have to have perfect concurrency. Now you can change some of these defaults, but that's the default behavior if you don't do anything and you just use the console. But what if you need more shards or more consumers on the same shard, right? You have big payloads, maybe you need several consumers. Well, this is where there's something called enhanced fan-out. And this came out last reInvent. An enhanced fan-out changes the mechanism from a polling mechanism, where Lambda is reading the stream, to a push mechanism, where Kinesis itself is pushing with a dedicated channel of throughput, 2 megabytes per second dedicated throughput per consumer, all the way to the Lambda service. And then the Lambda service is invoking your code as it receives the messages. So this gives you 2 benefits. It not only allows you to scale out more consumers, as much as you would like, many consumers can be accomplished here, but it also decreases the latency. So the latency with HTTP2-based delivery to Lambda would only be roughly 70 milliseconds. of how long it takes to get to the Lambda service. So you can achieve sub-second processing with Lambda if you're using enhanced consumers. Now, some best practices on the processing side. Well, first, we mentioned batching earlier. Batching isn't just for the producer. Batching has even more benefits for the consumer. So if you're worried about you have a kind of a low throughput stream, as I said, we're reading the stream by default once per second. So that means even if you can configure two knobs here. We have a batch size and a batch window. And the batch size is effectively up to 10,000 messages, and the batch window is up to 5 minutes. So if you configure those, you're able to hold on before you do that invocation to get more messages in your batch with one invocation of Lambda, more records in a single array, and decrease your Lambda cost by doing this batching. So it can be very efficient for kind of low volume streams where latency is less of a concern. Another key best practice, things to think about are related to retries. So the way the Lambda service works is when we get a message, we're going to automatically try to process the whole batch. But if any one of those messages in the batch fails, we're going to automatically retry the whole batch. We don't know which one failed, right? So the whole batch will be retried until either the whole batch succeeds or the messages fall off the stream, whichever comes first. So with that in mind, proud to announce that we have several new features that have come out just in the last few weeks if you haven't seen these. So you have the ability to configure and customize your retry and failure behaviors with Lambda. So not only can you set the retry attempts, the number of retries for a single message, but you can set the maximum age. And then whenever either of those is reached, what do you want to do with the message? We can automatically write it off to an SNS topic or an SQS queue as a dead letter queue. And then important to note is this final option here called split batch on error. That simply means if we get a batch, we have an error, let's not retry the whole batch. Let's say it was a batch of 1,000. We're going to split it in two. And in the next retry, each batch is now 500. And so if you set your retry attempts to 10, every retry we're dividing by 2. So if we discarded a message, it would be a very small batch size at the end that would be left. And everything else we would have been able to process. So these features are available today. Now, to add to that, you do want to be mindful of monitoring the ongoing stream processing. Right? So there's several metrics you want to keep in mind, but the most important one is called iterator age. And what this does is the Lambda service itself, it's the time between the last message the batch was written to this Kinesis stream and the current processing time of Lambda. So that delta is the iterator age at any given time. And this going up for a while is no problem. But what you want to watch for is if it's growing unbounded. So for example, if you had a large burst of messages at once, going up is expected. But if it never went down, perhaps you have a poison message that's holding up the whole stream, right? In which case, you should first start by turning on those settings I mentioned just now about retry behavior, failure behavior, all these kind of things. So these are just some things to think about. The other thing you can do, have any of you ever had this problem actually in production? Just in the audience? Okay, a handful of you. So for those who've dealt with this before, you used to know, you could increase your shard count, right? And then that'll create more concurrent instances of Lambda. But even in that case, the first shard, you're effectively splitting the shard. So the first shard has to finish processing before the other shards will take effect, and you'd have the new concurrency. So there's another feature available now called parallelization factor, or in the UI it's called concurrent reads of batch per shard, effectively, concurrent batches per shard. And all that does is it basically says set to 1 by default, but if you turn it, you can dial it up to 10. And what it means is the Lambda service will change that default behavior of reading one shard once per second, and instead have multiple instances of your code reading the same shard in parallel. But we know ordering matters, right, with any streaming, so to ensure we don't break ordering guarantees, well, our batches that will read in parallel, the order of the partition key, any records with the same partition key in that shard will still guarantee that ordering will occur in the right sequence. So effectively, your batches will be by partition key to ensure that we don't break the ordering. But without having to do anything else, if you just change these retry behaviors and you turned on the concurrent batches per shard setting, you could resolve such an issue very quickly now without any code changes needed. Now, Lambda, as we mentioned, has many great benefits for stream processing, but it doesn't always make sense. And so when might you not want to use it? Well, first, if you're doing a lot of stateful stream processing, Lambda's stateless, an ephemeral environment. So perhaps you want to use something like windowed aggregations. This is where you have counts and sums and minimums and maximums. For that, you want to use either Kinesis Data Analytics, which natively supports that, which we'll talk about, or maybe your own custom application using Kinesis Client Library or Apache Flink, something like that. At the same time, maybe you're buffering large amounts of data. You want to write to S3, big objects. Well, if you want tens of megabytes or something else, no reason to have Lambda be running to hold that compute when Kinesis Data Firehose has a built-in buffer already built in. So I mentioned latency of at least 60 seconds. Well, you also have the ability to control the buffer size and the buffer interval there, just like the batch size and the batch window on Firehose. So Firehose is going to be a better source for that kind of delivery. Now, speaking of Firehose, Firehose can also deliver and provide for you an ingestion, transformation, and loading pipeline just by itself, even without Kinesis data streams. So the way this works, you have the ingestion, just like we talked about before. You have the delivery to the managed destination with buffering and other things built in. And then in the middle, you have the transformation. So this is where you can tie in a Lambda function directly into the end-to-end pipeline. And that Lambda function could do many types of transformations. Some things that are typical would be enrichment, filtering, or conversion. So enrichment simply means maybe I'm taking some data like an IP address, I'm looking up the city and state with some lookup table, right, and I'm building out my enhanced object, enriching the attributes. Filtering would be I'm taking the payload, maybe I only want certain properties or certain objects in the array, I'm just going to take the others out and filter out just the data I want for my delivery. And then finally, conversion is as it sounds, where you're taking some data, maybe it's a log format data, you're completely changing the syntax and structure and shape of the data, perhaps JSON. So that's conversion. So best practices. On the processing world, a variety of things to think about. The first is the retry and failure handling. Whether you're optimizing for latency or for cost, you want to turn these settings on. You don't want to have your stream get stuck because you're reprocessing a bad message and lose data because it eventually expired, data off the stream. So you want to go ahead and configure these things. You also want to be mindful that anywhere along the data processing pipeline, there is a small chance that you could get the same message more than once. So we guarantee at least once delivery. And with that in mind, you want to be looking at doing idempotent processing, where if you did process the message twice, you haven't thrown off some business metric you care about. So you want to do some sort of idempotency kind of checks in how you're actually persisting that final data. Now, if you're optimizing for latency, enhanced fan-out is going to give you that dedicated throughput, right, with the extra consumers and push with lower latency instead of a poll. So enhanced fan-out is going to give you sub-second latency if you need it. At the same time, just increasing the shard count is going to increase the concurrency of the processing, and it's going to make things go faster. And even without even doing that, you could just change this concurrent batches per shard setting, and all of those settings alone will rapidly decrease your latency. But if the goal is cost reduction, with cost reduction, the enhanced fan-out consumers, they have an extra cost. So if you don't need them, and you have a very small number of consumers per shard, say 3 or less, well, in that case, just use standard consumers, the built-in behavior. There's no extra cost for that. And at the same time, use Kinesis Data Firehose to buffer data. Don't have Lambda do a lot of waiting around. Anytime Lambda's waiting, it's generally an anti-pattern. So buffer with Kinesis Data Firehose for delivery. And you can configure the buffer intervals and buffer windows, as well as the batch intervals and batch sizes with both Kinesis Data Firehose and Lambda, whatever's reading the stream. So storage is the next area to think about, right? You want to persist the data in a final resting place. And with that in mind, you still have data warehouses and Elasticsearch, but data lakes are more popular than have been in a long time. We've seen increasing rise of popularity. And for many reasons, S3 is kind of the center of gravity for a data lake. And one of the neat things about using S3 in a data lake is you can actually have a managed query service like Athena directly read the data on S3 without having to schematize your data at the time of loading it or anything else, right? Athena could just give you those results for ad hoc queries, and you just pay for the data you touch. So for those reasons and all the other integrations, data lakes on S3 are quite popular. And Data Firehose is the best way to write to S3. It's going to automatically do the buffering, right, and the optimal delivery. It can do compression, it can do encryption of your data, and a lesser-known feature of it is even a potential to convert the format of the data. So with Kinesis Data Firehose, you can actually convert transactional data, JSON-oriented data, row-oriented data, into columnar formats. And examples of this are ORC or Parquet. Those are columnar formats. And it can actually compress those files before delivery. So to summarize the best practices here, you want to be thinking about long-term usability of the data. And one of the key things we hear from customers is there's a lot of value in persisting the raw data itself. So take time to do that. A Firehose can automatically do it for you. And if you are going to write it to S3 and you do want to be able to read it with something like Athena or Redshift Spectrum, think about how you're going to partition the objects over time. So you're going to write them with S3 prefixes, which is natively done with Firehose too and can rotate those prefixes. And think about the columnar formats. Just by using partitioning and columnar formats, the cost of queries with Athena can go down by over 90%. At the same time, on the cost side, right, you want to do the buffering we mentioned before. Compression, the less data you're storing in S3, the better. But by doing this buffering, you're also saving costs because the fewer API calls you make to S3, you're really more focused on the storage cost. If you were writing teeny objects to S3 at high scale, your cost of those put object calls could actually exceed the storage itself. So that's why you want to be thinking of putting these bigger objects together and buffering. And then, of course, Firehose out of the box will do Redshift best practices like the copy command. But you want to think about how you're loading that. And then once things are in S3, if you care about cost, you don't need the data forever. Or maybe if you do need it forever, you don't need it in the same hot, warm storage forever. So you could transition it off to colder storage. And then finally, we have analytics, right? So on the analytics side, there's many different offerings here available for you in AWS. QuickSight for visualization, SageMaker for AI and ML, the other managed AI services, Glue, Athena, and more, as we mentioned. But the one we haven't talked about is Kinesis Data Analytics. And what this service does is it allows you to do real-time analytics on the data while it's in the stream. So it takes a stream, it does your real-time calculations, and it outputs the data to another stream. And the way it does this is either through SQL or a Apache Flink application written in Java. So if you already have Flink-based applications, you can just upload them to data analytics. But for SQL applications, we have something called windows. And windows are used in the Java world too. And windows are effectively what allow you to calculate the sums, the mins, the maxes, and so on in the aggregates that you care about. It's the window of time and the window of data you're looking at. So to show you an example of this, this is a Kinesis query where you're writing so many. This is a query to basically look at what are the calls per IP address in 1-minute intervals. Right? So where you might normally be used to a group by clause in traditional SQL, here you have a windowed by clause that's saying, hey, I want a window by partitions of source IP address, and I want them over 1-minute intervals. And that's all it takes to actually start emitting another stream with all the data per IP address, the number of calls per minute. And then you can now take that stream and write it with Firehose to the final destination or real-time graph or whatever you'd like to do with it. So to put all this in context, to show you an end-to-end example architecture, you're always going to have a source. So the source may be a mobile device, web server, IoT devices, whatever they are. Then you're ingesting the data. So in this example, we're going to Kinesis Data Streams, but it could be Kinesis Data Firehose, right? Once you have the data in the stream, you could do fan-out processing. So Kinesis itself can consume that stream. And so here we actually have Kinesis Data Analytics reading the stream, calculating those real-time metrics. And in parallel, we want to not only persist our raw data, but also do our transformation in line with a pipeline just built with Firehose. So an ingest, transform, and load pipeline. And that's down here at the bottom with Firehose. So all that could be done end-to-end just using Kinesis and serverless offerings. Now, to give you the best context of this, and for someone to share how you do this in production at scale, I'd like to welcome Anushri and Ranga to the stage and to talk to you a little bit more about the metrics pipeline of Comcast X1. Now, for those not familiar with X1, here's a quick clip on what the service offering does.
just keeps getting better. How you watch it does too. This is Xfinity X1, featuring the Emmy Award-winning voice remote. Streaming services without changing passwords and inputs. Live sports with real-time stats and scores. Access to the most 4K content. And your movies and shows to go. The best TV experience is the best TV value. Xfinity X1. Simple, easy, awesome. Xfinity, the future of awesome.
Well, thank you for having us. At Comcast, we are extremely proud of X1, which is the platform behind our premier pay TV application. X1 is available to tens of millions of residential customers, as well as tens of thousands of small, medium, and large businesses. And finally, hundreds of colleges and universities. Today, we're excited to share with you how we, by using AWS serverless streaming, are able to keep Xfinity brand promise, to connect people to the moments and experiences that matter most. My name is Ranga, and I work together with a team of 8,000 developers, product managers, and network support professionals who are responsible for maintaining X1, parts of which we just previewed for you here today. And I'm proud to join a key member of our technical team, Anushi Shenoy, who's the Director of Software Test Engineering, and whose chapter has been critical towards building some of the capabilities that we're going to share with you here today. Now, X1 is available to customers not only within the Comcast footprint, but is available to millions more through our syndication partners. So whether you are a subscriber of Cox Communications in the US, or Shaw, Rogers, and more recently, Videotron in Canada. Now, to deliver this service, we employ a hybrid private-public cloud with about 40% of our workloads running in AWS. The architecture of X1 has business logic and presentation layer running in the cloud. As a result, we require tens of thousands of VMs, and each VM maintaining thousands of stateful user sessions. And because we have applications that are latency dependent, such as Xfinity Voice, we maintain a persistent connection between each set-top box and its corresponding stateful user session in the cloud. So that means over several hours every day and across all the time zones that we serve, there are tens of millions of persistent connections between set-top boxes and AWS sessions. Because this is a managed service and we are accountable to an SLA, we incur an escalating schedule of customer care call impacts depending on whether a customer calls or depending on whether we dispatch a service professional. In worst case, depending on whether we actually lose the customer. So today, we want to share with you how we evaluate the quality of a release before we launch it into production. That essentially breaks down into two specific work streams. The first thing is we derive an objective score for quality, a Canary score. Then the second, we run that Canary score against a number of cohorts and then determine whether we launch. This is our release quality check. So the way we evaluate the quality of a build is we take 3 cohorts. The first one is our product development team, which we call early look. And we calculate a Canary score over that subset, which is usually about 5,000 subscribers. Then we go to a randomized sample of 5% of our overall user base before going to 20%. Now, depending on the nature and complexity of each release, the release quality check can run from anywhere between a few hours to a few days.
So the Canary score that we just discussed to evaluate the release quality is basically an A/B comparison between the metrics of the previous version and the version that we want to send out. So when we say the metrics, what we are evaluating, like any other product, is basically quantifying the user experience and the health of the infrastructure that hosts these versions. Now, when we say user experience, how do we quantify it? It is latency. So latency being you have a key press and time taken to launch a screen and to tune to a channel, play back a WAD or a DVR, launch an application. So what is the time taken for this? In some cases, also, when you connect your set-top box, the time taken to set the connection and be responsive to the first key press. So that done, we have quantified the user experience. We, of course, look for even errors, like tune errors, playback errors, and things like that. With that, the health of the infrastructure, it's actually on the heap utilization and the CPU utilization for the versions that we are hosting. Now, with the metrics defined, what we needed to do was collect these metrics and then go ahead and run our Canary scores on that. But since, as Ranga mentioned, we are supporting millions of devices on tens of thousands of VMs, the requirements for our pipeline was supporting millions of records per minute, generating these AB sets, and our comparisons are on time series data, so these had to be store the time series data. Now, the nature of our application is, since it's generating so many records per minute, we had to be performant. We should be able to scale. With new features going out, we can increase the number of metrics that we are evaluating the performance on, as well as with increasing customer base, the number of metrics that are generated will also be huge. Now, while doing all of these, we had to be economic.
Now, Justin laid out a 4-phase process with ingest, process, store, and analyze. And our architecture effectively maps to these sort of 4 phases. The key challenge that we had, however, is on the one hand, we generate a lot of events, right? We generate a lot of events. Then on the other, we have to think about the economics of how we generate just enough events to be able to extract enough of the scoring to generate our Canary score. So when you think about the VMs that generate the events from our X1 user sessions, we see a volume of between 9 to 27 million events per minute. Now, not all of these events are required for Canary scoring, where we're focused just on performance and error metrics. And when we take that subset, that reduces to about 2.5 to 5.5 million events per second. So in order to meet our own objectives, which is where we wanted to manage the way we ingest, so we wanted to buffer, we wanted to rate limit, we chose Amazon Kinesis data streams for that ingest. However, our key challenge was that our data is incredibly bursty, right? It doesn't come in smooth during the ingest period, but it's incredibly spiky. So let's talk a little bit about the data generating process, which is driven by how users consume video. So 3 specific things and 3 specific qualities matter here. The first one is because we're a national operator, our prime time runs through multiple time zones. The second, even within each time zone, we have this day-long escalating pattern which peaks at prime time. And then we have a second pattern, a second aspect of our time series data, which is this intra-hour pattern that's driven by linear programming boundaries. So if you're watching linear TV, programming changes at the top and the bottom of the hour, and you're likely to do something. You're likely to change your channel, search for new content. And that is where we generate most of our events.
So the granularity that we wanted to work with was on minute basis granularity. But as Ranga mentioned, all the data that is being pushed by these VMs onto the ingest stream, they were at the top of the minute. So even though we say it is a minute level granularity, it was coming as 5.5 million events per second. Now, if we go ahead and design the stream for this level of concurrency, it would be a huge stream. Whereas with the granularity defined as per minute, what we could do is we could stagger these events that are coming in over the minute. The other thing that we had considered was the record size, and Justin did mention that. The record size was very, very small. And we were well within the limits per shard limits per second. So what we decided to do was batch those. So batch records and then send it over the minute rather than maintaining the second level granularity to the stream. And that's what we did with our optimizations. We batched the data, and based on that, with minute granularity, we sized our stream. But even with this, though now on a minute level, our stream is utilized, due to the 3 different patterns that Ranga mentioned, which is the prime time, non-prime time, and reboot window, mostly during the non-prime time, our streams were going underutilized, and we were still paying for it because the streams were constant size. So what we did is we scaled the stream, and with set schedules, we use the Amazon APIs, and went and said that twice in 24 hours will scale from X to 2X. So during prime time, go full scale, have 2X number of shards in the stream, and non-prime time go down and have X number of shards. So with these optimizations, now we had the data flowing into our stream. And the next step for us was generating the A and B data sets. So A and B data sets, the way we thought about that was, there are these group of VMs which are hosting version A and a group of VMs which are hosting version B. Of course, the percentage rate is not the same because we have a phased rollout. So we decided, let's take a subset of those VMs, and it was kind of 25 VMs of hosting version A and 25 VMs hosting version B, and then group by that for all the metrics that we have identified. So our process looked pretty simple, store looked pretty simple from a design perspective, use Kinesis Data Analytics, which reads from the Kinesis data stream, and group by the set of hosts that we have identified. And once the A and B sets are created, put it in the Kinesis Data Firehose, deliver it via that into Amazon Elasticsearch because we had time series data. The challenge that we had over there was the record formats were pretty disparate. In fact, if you look at the raw event, what basically happened is, if we look at screen latency or tune latency itself, that event had multiple data points for the same metric. And it was coming in as a text format. Whereas Kinesis Data Analytics prefers a structured format. So think about a CSV or a simple JSON. So before our Kinesis Data Analytics picks up the data, the events had to be transformed. So now we designed our process to look like this, wherein we have a Lambda that gets triggered by the Kinesis data stream, and it converts it into a simple JSON format, puts it in another Kinesis data stream, which is called the transform stream. And then from there, we pick up, the data is picked up by the Kinesis Data Analytics, and the time series data is generated. And this is how our entire process and store pipeline looked like. Now, a couple of challenges that we had. Of course, we had to do real-time aggregation, again, maintaining the 1-minute granularity. And that meant that our processing for the Lambda, as well as the Kinesis Data Analytics, needed to be sub-second. All of this while maintaining the cost. So the optimizations that we looked at. Now, though I said the Lambda was just transforming, it wasn't just transforming for us, it was enriching the data also. And while we were enriching the data, that means the metadata that we are adding into the events that are coming in, they were coming from a Redis database. So we had connection strings to a Redis database. So now every Lambda that gets invoked, if it initializes it, it was spending time during initialization. So we went and used something called the execution context of the Lambda. And the first Lambda that gets invoked, it will go ahead and initialize the connection string, and subsequent Lambdas will now use this execution context. So we save time in initialization. Another thing, again, Justin alluded to it, we batch the data. So the Lambda is not getting triggered at every event that comes in. It gets triggered on a batch of events. And with some experimentation, as the Lambda gets charged based on the invocation duration as well as the number of invocations, what we did is we found the perfect batch size for us and assigned it, or gave the Lambda enough memory to process it quickly. To avoid operational overheads also, and I'll I'll describe the other operational overhead that we might have found later on. But what we did was, instead of putting the configs inside the Lambda, what we did is we put them in environment variables. So you don't have to, anytime we have to change the configuration on the Lambda, you don't have to change it in the code and deploy it again. It was an environment variable change, and the next invocation would pick it up. Best practices for Lambda was, again, avoid sleep times and long-running API calls. Now, our Lambda was pretty much processing everything real-time and doing good. But still, our metrics didn't look right when they were going into the store. And when we looked at analytics, what we found was something called time behind in millis, which is similar to iterator age mentioned by Justin, was kind of 2 hours. That means even though we are saying that process things as they come in and maintain the minute level granularity, the processing was going ahead and considering metrics that were there in the pipeline since 2 hours. So it's not that minute's aggregation. It is basically aggregating something that is arriving at that minute as well as has arrived like 2 hours back. So when we looked at this particular time behind in millis and went and researched further, we found something called input parallelism in the documentation of Amazon. And that stated that if your time behind in millis is huge, what you should do is you should break the way you pull the data or the analytics picks the data. So rather than picking everything as one whole chunk of data for that minute, go ahead and put parallel threads. And this is what input parallelism was. So we put an input parallelism on 5, and again, the processing came down. The time taken to process came down, and the time behind millis was also pretty good. All these metrics, along with our write throughput provision, read limits, time behind in millis, iterator age, invocation duration, all of these things that we monitored, it was via CloudWatch. Now, with the process and store done, we had the data available in Elasticsearch. So it was time to now analyze the data. So the data is sitting in Elasticsearch. First thing for our application, which is a Java application, was to fetch the data. We fetched the data, but this is where we hit the first glitch. Because of the way we store the data, or rather the way we generated the metrics. So for screen latency, instead of saying that this is my average screen latency or this is the 95th percentile, what we stated was we had 500 different buckets, and in these different buckets we said that so many customers see 0 to 10 milliseconds latency, and X number of customers see 10 to 20 millisecond latency, and that is how we had 500 different buckets. So when we saw the data, we had 500 A sets and 500 B sets for screen latency. So additional processing was required, wherein we need a single A and a B set. And this is when we introduced the process of something called normalization. We normalize the data. So something similar to Canary score algorithm, a little bit tweaked. We went ahead and applied on these 500 buckets and converged the data. And it became like 2 A and B sets. Now, when you look at the manual performance testing that we do, what we do is with 2 time series data, if you have similar spikes in the A set and the B set, we cancel them. And then we calculate the change percentages, the direction of the change, and say, OK, A is better than B, or B is better than A. Now, to logically do it, what we had to do in this algorithm was sort the data. So we sort the data so that we put similar points together. And now we started calculating the change percentages between each and every data point that we have in the time series data. And based on the direction of the change and the change percentages, we started penalizing those change percentages. And consolidating all of that, we got a Canary score. Now, this is done for one particular metric. We did it for all the metrics that we found. And now we had a bunch of Canary scores. The objective, however, was to get a single Canary score for a release that is going out. So just like GPA scoring for any college-going student, what we did is we did weighted averages and got a final score. Now, this tells us whether to go ahead with the version or not. So if you are closer to 0, that means you are similar. So the baseline and the test, both the versions are same. If you are moving away from 0 towards the positive side, that means your test version or the next version is performing better. If you are going towards the negative side, that means your baseline is better. You better take a look. Don't go ahead.
So what was built as a sort of single-purpose pipeline for evaluating the quality of a build quickly became, reusable for other use cases. So in the initial use case, we would look at every single release, and we would use the Canary application to schedule some Canary tasks and then launch the metrics computation algorithm for Canary scoring. However, we found that we're actually able to reuse the same pipeline for multiple use cases. As we indicated before, we run a hybrid private-public cloud. So one of the use cases was evaluating the relative performance of the same build deployed in one sort of data center compared to another. Or as we've started to migrate away from some of our monoliths, comparing a performance of an application which is dependent on a service implementation in a monolith versus the one in microservices. So we started increasing the number of parallel tasks that use the same framework, and we reached our next sort of threshold.
Yeah, so that was our next challenge. So this is how we designed the entire Canary data pipeline. But the problem that we had was when we had to run parallel canaries, and this is the way we were going ahead and defining our SQL query inside the data analytics. We were using 50 VMs, and with input parallelism, repeating those 50 VMs in our group by clauses. And we started hitting the character limit in the SQL query itself. That means every Canary job that comes in, you have to have a separate Kinesis Data Analytics and a Kinesis Data Firehose. So that was fine. We started, any Canary came in, the application would spin a data analytics and a data firehose. But the problem that happened is once we hit the fourth job, the metrics were getting skewed. And this was, even though with input parallelism, we were seeing the time behind in millis increase. And that was because we were hitting the read limits on the Kinesis data stream. So this is where we started using enhanced fan-out, which allowed us to increase the concurrency. So we said that any job that comes after the third job gets its own read limits. So put an enhanced fan-out over there. This works. Concurrency is maintained, but it was impacting cost. So we went back to our ideation board and tried to figure out the issue that we have, and the reason we are spinning up so many data analytics and Firehose is because of a group by clause and putting 50 VMs in there. Is it possible for us to go ahead and reduce the size of the SQL query? So we said, OK, let's remove the host itself from the group by clause. And as we already enriched the event that is coming in, let's put more markers into the events. So once we figure out that this host is participating, or this VM is participating in the Canary scoring mechanism, the event that comes in, let's put some markers saying that consider this for Canary. What kind of Canary are we considering it for? This is additional metadata. What is the job ID? And then what is the differentiator? Is it supposed to be considered for baseline, or should be considered for test? And with that, this is how our architecture started looking like. So our Canary application, we go ahead and schedule a job. Once the job is scheduled, it identifies the hosts or the VMs that will participate in the Canary scoring mechanism. This metadata is stored into Redis. We go ahead and now update the environment variable of the Lambdas, stating that there's a Canary job coming, start enriching. So next invocation onwards, it will pick up the data from Redis, enrich it, put the transformed event into the Kinesis data stream, the transformed stream. And now we have a single data analytics and a data firehose, which is handling any number of jobs that we go ahead and create. So pretty much, the more number of jobs we create, the more we save. So.
Fantastic. So, and I think at this point, we just wanted to share a few lessons learned at a really high level. Prior to our adoption of AWS serverless streaming for this pipeline, we had a fairly functional pipeline that used Flume, Storm, and Elasticsearch. And it had a number of tenants, each with different business requirements and running different data models that proved so difficult to refactor that after 6 months, we basically gave up. Subsequent to adopting AWS serverless streaming, we were able to take that same event stream and using Kinesis Flume client libraries, stand up a pipeline in just about 2 weeks with a handful of developers. And since we've really adopted this pipeline, we have been able to sort of execute on a run rate of about 100 major and minor releases per year, with each release running about 5,000 Canary scores per release. And that's been really critical for us to do quick go, no-go decisions, and quite frankly, really reduce the number of change-related outages. We've also been able to extend, as I said, the number of use cases that we applied to the same pipeline. So whether it's evaluating different data centers, evaluating different service layer implementations, or even for anomaly detection. And in our competitive video space, it is incredibly important for us and for our cross-functional teams to be able to innovate at scale. So looking at multiple features across our product offering and be able to deploy new code. And with our sort of partnership with AWS, our ability to do this release quality check at scale across multiple teams in a cross-functional manner has been a critical part of our ability to just stay ahead of the competition in many respects. And with that, we want to thank you for taking the time to spend sharing our journey with us, and AWS for a strategic partnership helping us keep Xfinity's brand promise to customers.
Thank you.
Thank you, Ranga. Thank you, Nusri. So just to conclude briefly, we do have several other sessions going on this week: asynchronous patterns, stream messaging, serverless design patterns and best practices. Encourage you to check these out. There's also new training available for serverless from AWS Training and Certification. If you haven't seen it, it's online now. And then, of course, we thank you for all joining today and would appreciate if you could take the time to fill out the survey. Thank you very much for your time.